I'm Chris Mink. I teach philosophy of science in the Department of Philosophy here in the Faculty of Arts and Humanities, and I'm a former director of the Rotman Institute of Philosophy. We're delighted to welcome you here tonight, both in person and online, for the annual Robert and Patricia Duncanson Lecture. It's wonderful to see so many people from London here, and also to welcome those who are joining us from afar online. I want to give a special welcome to students joining us today across the university, and those who may have learned about the event from the Rotman Institute or from Western alumni. And welcome especially to the Faculty of Arts and Humanities. Western University is located on the traditional lands of the Anishinaabeg, Haudenosaunee, Lenapewayak, and Attawandaron peoples on lands connected with the London Township and Sombra Treaties of 1796 and the Dish with One Spoon Covenant Wampum. This land continues to be home to diverse indigenous peoples, First Nations, Métis, and Inuit, whom we recognize as contemporary stewards of the land and vital contributors to our society. The Duncanson Lecture celebrates our faculty's dedication to fostering thought and discussion on the significance of humanities scholarship. It highlights our commitment to positively impact complex contemporary and future challenges. I'd like to take a moment to acknowledge Tim Duncanson, who's joining us online, and to members of his family who are here tonight. Thank you again, Tim, for your thought leadership at Western and your continued support of research grounded in the arts and humanities. A quick word about the structure of this event. Dr. Rovelli will speak for about 35 minutes. There'll be a Q&A, which I'll help to moderate, and then we'll have a reception next door, and you're all welcome to join us there. When we approach speakers for this lecture, we're looking for leaders who bring a unique approach grounded in humanities scholarship to big, challenging questions. This year, building on the strengths of our faculty, and indeed of Western as a whole, we are keen to profile someone who can speak to the intersections of science and storytelling. Nabokov once said that a great writer must have the precision of a poet and the imagination of a scientist. It's a great pleasure to introduce Carlo Rovelli, this year's distinguished Duncanson lecturer, who exemplifies both qualities. Carlo's enormous creativity has led to contributions in many areas of physics. He's one of the founders and leaders of loop quantum gravity, one of the main approaches to developing a theory that combines quantum mechanics and general relativity. But his interests extend far beyond physics. He's published a series of beautifully executed books for general audiences within the last 15 years that display his poetic precision and intellectual range. They're meditations and reflections that start from what we have learned from physics, but explore the ramifications of these insights wherever they may lead us, including rethinking our own nature. These books also display Carlo's generosity and idealism. Alongside the impact of Carlo's research, he's been an inspiring leader and mentor for many of us in physics and in philosophy. I had the great good fortune to first meet Carlo as a graduate student. I got to learn general relativity from one of the modern masters. And my colleagues and I here at Western have benefited in so many ways from his presence here alongside his brilliant partner, Francesca Vidotto. Carlo has inspired us all to do better work through his challenging and insightful questions, but also through his encouragement and by exemplifying a way to do research that tackles deep questions. So without further ado, please join me in welcoming Dr. Carlo Rovelli for today's lecture, Come With Me Inside a Black Hole.
Thank you, Chris, for these very kind words and deserved. And let me actually take this opportunity to thank the entire university here, because the way I've been received here has been marvelous, and I've found an extraordinary intellectual environment, which has been very enlightening to me. The time I spent here has been wonderful. And thank you all for being here, for coming, and hope you're ready and try to take you inside a black hole. That's it. That's the aim. What I want to do with this trip is two things, quite different. One is to tell you what we know about these things, black holes, because they're remarkable objects. I'm sure you have heard a lot about them. I hope I'm telling you something more about their strangeness and the beauty also. And I also want to tell you how and why we think we know all these things reliably, what we reliably know about what they are. The second part, I will break this in two parts. The second part is not about what we know reliably, but the kind of open questions that black holes put in front of us, what we do not know about them, and how we're working trying to figure out how to answer these questions, and why these questions are important, and regards our understanding of reality, our understanding how reality works. So please keep this in mind. I mean, the first half will be, yes, that we know. As far as we know something, we know this pretty well. The second is a research in course. And in both cases, my aim is to sort of try to show you how theoretical work in fundamental physics happens, and how it has happened, and how it's happening now. And I hope I need you. Sorry?
Sorry.
It's not good. It's not strong enough. It's not. It's too low. I'm happy to use the, if it works better. 1, 1, 1, 1, 2, 3. Better? Can you hear me up there? Okay, good. So I need two things from you, or three things. I need your attention, of course, and I need your imagination in this travel. And the third thing, I need you to be open to the idea that reality is quite strange and different from what we're used to. All right, so that's a black hole. That's an actual picture of a black hole. And let me start this way. Perhaps the most spectacular discovery in the science in the last 10 or 15 years has been that black holes exist. They're real, they're out there. And not only that, the universe is full of black holes. So it's not just there are 2 or 3 black holes out there. There are 100 million, 1,000 millions, billions, hundreds of billions of black holes out there in the universe. The universe is full of this stuff, all over. They're different. Some are small, relatively small, some are bigger. The small ones are that we have seen are sort of the size few kilometers, like London, Ontario, not the other one. The big one, this one, are much, much bigger. So they can be larger than the Earth. This one is larger than the solar system, probably. And there are some which are 1,000 times bigger than this. So these are compact objects, but colossal. They can be colossal. The small ones, the one of few kilometers, they're all very massive, enormously heavy, if I can use this language. So the one of the size of London are already more massive than the sun. There's a very much concentrated amount of mass in a small. The 1 billion times larger are billions times the sun. So they're just unimaginable objects with respect to our common experience. they're remarkable, and you will see. I'll describe you why they're so remarkable. Let me anticipate this. The most remarkable aspect, and perhaps the most fascinating part of all this story, is that it's not something we have looked around and discovered. Oh, what is that? Look, strange is a black hole. It's the other way around. These are objects that were first computed mathematically as predictions of a theory. Nobody believed them. Nobody believed the existence of them. When I was at the university, so before like Chris, when I was a student, it was my time to be a student at the university in the general relativity class, I remember distinctively a class about black holes and the teacher and the book I was studying saying, yeah, it's a beautiful prediction of a theory, it's Einstein theory, general relativity, but these things probably don't exist. They're too strange to exist. I mean, come on, how can you compress the mass of the sun in a few kilometers? It's not going to happen. Well, it does happen. Okay? So these objects were predicted, and it was predicted. So Einstein wrote his theory 110 years, 109 years ago. The equations are there, and then slowly working through the equations, it became clear, it took long, decades, to look at the equation were predicting the existence of this object. And people were very surprised. Like, come on, I mean, it's too strange to exist. And then the first hints were in the 70s, but very few people took them seriously. The 80s and 90s, this century, people started to believe it a little bit more. More people started to believe it, and now there's enormous evidence. We see exactly what is predicted by the theory. I mean, look at this object. This is an actual picture of something in the sky. The theory predicted that we were going to see something like that, and we see something like that, exactly like that. The theory predicted that we were going to see gravitational waves with a very specific curve, and we see exactly that specific curves, and so on and so forth. So, fantastic. It's one of the cases, there are many, but this is perhaps the most beautiful of all, where thinking about how the world could be, trying to put together the hints, led Einstein here to write equations, and this equation in turn gives predictions, and the prediction turned out to be correct. Okay? So that's one black hole, a specific one, is called Sagittarius A star, and it's one of the big ones, not one of the biggest, but the big one, but it's one we know particularly well because it's in our galaxy. In fact, it's in the center of our galaxy. There are many more black holes which are closer to us, a few light years away, like the stars around us. Many of these which we know, but they're smaller. This is the center of our galaxy, is big. It's one of the big ones. So it's easier to see it because it's big. So I want to take you there and inside there. So imagine we start and we go. So here's where imagination, has to come in, of course. So imagine we're in a starship, or I don't know if you're a different generation, on a broom flying with the sky, whatever you want, and we go close to this thing here. So we cross the galaxy, we go to the center of the galaxy, and we come near this. And what do we see? We see that, because that's a actual picture. This picture was taken by telescopes, by radio telescope, by a collection of radio telescopes all over the planet. It's a beautiful enterprise just to take this picture. So we see that. It's sort of a ring. Okay? So why do we see a ring? You might imagine, okay, so we see the ring because there's an actual ring there. So if we moved on a side, no, you told me not to go on the side. If you go on a side, we would see not the ring, but no. Black hole, wherever you go, you see a ring, even if you turn around it. Because that's not the actual shape of the black hole. That's an optical effect. It's an optical effect created by a black hole. So let me tell you why you see a ring. Okay? This was predicted theory. The theory predicted that you would see a ring. So the point is that these are very massive, very heavy. So the gravity is very strong. And one of the consequence of Einstein theory is that light falls toward heavy things. And this is because it's really an intuition by Einstein. Things that have mass fall. Light has no mass. But you'll know that E is mc squared, the energy is mass. So if mass fall, energy should also fall, and light has energy, so light also should fall. So Einstein worked this out, and you can compute how much light curves. But these are very compact. So light curves a lot near a black hole, very, very much. So it works like a lens. It changes the direction of light a lot. So imagine you have a very massive thing there, and around you have hot matter, just whatever makes light. So some light, it's produced here, okay? It comes to you, but it also goes around. It's bent by the mass and comes to you. So some comes like that, and some bends around. But another one comes directly, but also bends around. And some even makes two turns and bends around. And some from here and bends around, okay? So all around the thing, you're going to see light, which is some direct light, but also light from all over that bends and comes to you. So you're going to see a ring around the mass of light getting to you. But if you're somewhere else, it's the same. So wherever you are, you see a ring. This is not, the black hole is inside. It's a ring, is an optical effect due to the enormous attraction of this very massive thing that bends alive. Okay, so we go there, we see this, okay, we open the window of the starship, we look around, wow, great image. And now we go closer. We go closer, 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 okay? Now, this is very heavy, so it attracts us. But suppose we have rockets and we keep at a distance. We stay close to it, but we wait before entering, okay? We get close to it, very close, stay there with big rockets. And now we wait, and that's the first spectacular thing that happened. We're in touch with our friends back home, right? So we receive signals. And imagine that every day we listen to the news, okay? Whatever, CNN, Fox News, whatever you want. You listen to news. As we get closer, we receive the daily news not every 24 hours, but every 23 hours, every 6 hours, every 2 hours, every 1 hour, okay? Every 10 minutes. So every 10 minutes, we receive the news of 1 day later. So if you want to know what's going to happen in the next elections in the US, or how it's going to happen with the war, just go near a black hole, wait 10 minutes, and you get to know the future. Okay? Of course, it's also true vice versa. Our friends on Earth are looking at us, and they receive our news. If we send every day, every 24 hours, we send, okay, we're still far, we're still outside, okay? But they receive it not every 24 hours, but every 2 days, every 5 days, every week, every year. This is the effect which is called time dilation. And it's spectacular. So time goes sort of slowly. The more near you're a black hole, the more slowly goes time. Not in the sense that if you're there, something funny happens. If you're there, you have breakfast in the morning, everything is normal. But with respect to what happened on Earth, things go very, very slowly, while on Earth go faster, and vice versa. With respect of Earth, things happen rapidly, but there happen things slowly and slowly. Now, this is an effect which has been observed, measured. It's also observed here on Earth in the laboratory, but they're very teeny. Near a black hole becomes very, very large. And we see it. For instance, the light that we receive from there has a wavelength, which the frequency of the light is much slower than what we would expect normally, because time there goes slow. And the more you get close to the surface of the black hole imagine is a ball, okay, round, black. And the more you get close to it, the more things slow down. If you get very, very close, what you see is just, your friends were there, you just don't move anymore. But again, we're there, we fly there, and everything is normal. So we go in, now we cross, now we're inside the black hole. And we keep seeing the Earth, of course. We keep receiving very, very fast. We know what's going to happen, in a century, two millennia after the nuclear war. I mean, everything very fast. But our friends don't see us anymore, okay? Until somehow we might come out or not. Okay? We're in. Second effect, okay? Now we're in. I told you about time dilation. I'm going to tell you the other remarkable effect inside a black hole. So we're inside. And as I said, in this black hole, from the outside, the size is, this is a pretty big one, as I said. But imagine a given size, and imagine a few kilometers. So if you have a ball with a radius of a surface of a few kilometers squared, inside you expect a few kilometers cube of space, right? You go in, and there's much, much more space than what you expected. So when you're inside, the space is enormous, and you keep going. You know these fairy tales that the two guys walk in the forest, and there's a little hut, and they go inside the little hut, and there's a huge hole, and then there's another hole, and the gardens. It's all this space, and then they come out, and it's just a little thing. Well, that's exactly what a black hole is. This is a distortion of space. The usual intuition we have about space, three-dimensional space in which we are inside with immersed, is that if you see a ball inside, you know the volume. Well, that's because this is the geometry around us. But the geometry of space can be different, and inside a surface, there can be much more volume. It's like, if you're a little ant walking on a square, and you're always used to the surface of the square, the main square of your town, then you find a little hole, and there's a huge space inside, okay? Because the ground is not flat, there is something inside. So a black hole is something like that, but three-dimensional. Now inside, what's a space inside? Inside the space is a shape of the space. For those of you, I know there is somebody here who knows general relativity well, so I should be careful of not saying wrong things. In a proper foliation of the inside for the expert, the space inside is like a long, long tube, like a cylinder. Okay, so you have the entrance, which is this round square, and then it goes very, 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 very long. And the older the black hole, the longer it is. It's not infinite, but it's super long. So it's sort of like a tunnel. It's big, but not big in all directions. It's big just in one direction. The other direction is small. Okay, so it's still round, and this is very much like a, what's the name in English? The thing to un entonnoir, to put milk in a bottle. A funnel. Okay, it's like a funnel. It becomes long like that, right? Funnel is also something like, you have the border of it, but the inside is bigger than what would you expect if it was flat. So inside that thing, it's like a funnel, which goes very long. Now we're inside. So we are inside this funnel, and we're surprised by the time dilation, space dilation. And the third thing we discover, I'm still in what we know for sure. Huh? I'm still in the reliable part. Every relativist who knows the theory says, yeah, that's what we expect. So inside, we've been surprised by the time dilation, which is surprised with the normal space. We are inside, and now, if we try to come out, we can't. Okay? Even if we turn our rocket at maximum, we just can't get out, because in a sense we are just trapped inside. But it is worse. We realize that this very, very long thing, we can move, can still move with the rockets. But the size around us, not the long size, the radial, it's shrinking. It's becoming smaller. So we say, oh shit, it's becoming smaller and smaller and smaller, and it's squeezing us inside, okay? And it's squeezing more and more and more and more. So we're gonna die, but we're gonna die nevertheless, even outside, everybody dies. But if we just believe the theory, this squeezing is increasing indefinitely. So at some point, this is called the singularity, the famous singularity of the black hole. Careful, the singularity is not a place, it's not down there at the tip of the funnel. The singularity is at a time. So we're inside, and this thing is shrinking around yourself. Like, you know, this room, the singularity is not in a corner. It's that the entire room, at some point, at some time, is shrinking. But this is as far as the theory is reliable. Einstein theory is reliable. Because when it becomes very small around us, assuming we are, you know, imagination here, we have some super kryptonite thing around us that is surviving all that. Okay, so we're not being squeezed by that. At that point, we have very good reasons for not believing Einstein theory anymore. Why? Because, so you all know there's quantum mechanics. Well, nobody's talking about quantum mechanics. This is 100 years of quantum mechanics, 2025. And Einstein theory does not take quantum mechanics into account. So if you want to know what happened before the complete squeezing, we have to take quantum mechanics into account. And this is a simple calculation that can be done to know when quantum effects come in. You just have to do an estimate, and you see that when the shrinking, it's great, the curvature of space is great, and that's exactly when you expect quantum effect to come in. So now if you want to know what happened, Einstein theory is not good anymore. Okay? Einstein published his equation in 1915, and in 1916 wrote a paper saying, of course, this is not the end of the story because there's quantum mechanics. So the equation that Einstein wrote are not going to be the end of the story about gravity, space, and time, all that, because there's quantum mechanics. And understanding the quantum aspect of what happened there, the squeezing, you need a quantum theory, a quantum version of Einstein theory, and 100 years have lapsed, a lot of people working on that, including me, and for the moment, nobody has been able to find a theory that convinced everybody else, or find a theory that it is reliable, proved, like Einstein theory is, okay? So I jump to the second part of the presentation here. Now I'm not telling you what we know with great confidence, but we're not in the dark, because we haven't found a theory which is reliable and convincing everybody, but we do have tentative theories. We have ideas, okay? We have equations written down for a quantum theory corresponding to general relativity, to Einstein theory. And that's been the sort of the work of all my life. I've worked for constructing one of these theories. And that's why I'm so attracted also by this object, because inside there is exactly a phenomenon which requires a quantum theory of gravity to be understood. Okay? So a big effort has gone, me and a lot of colleagues, to understand what's going to happen at that point. And now I'm going to tell you what happened at that point. How much time I have? Yeah, I'm still doing well. So here's intuition. If we let ourselves fall into a black hole, go in, we're falling into a black hole. The black hole itself, most black holes formed because the big star, not all, we don't know how old black holes formed, but most, we know for sure that a big star, like the sun or bigger, the sun is much more massive than the Earth. So there's much more pressure. Pressure could squeeze any rock down and squash everything. But since it's burning, the heat keeps it open. But when it stops burning, because the fuel is ended, it falls and collapses and forms a black hole. So it's a falling. And I said that the inside of the black hole, this long tube, is itself squeezing. That's also falling. It's like space-time, which is falling. This funnel is a continuous falling, it's shrinking for falling. All right, so suppose, think about falling in your experience. And something is falling and hits something. Okay, imagine you have a ball, you let it fall, hits the ground, what happens? It bounces back, right? That's a normal thing that can happen when something bounces back. Other things can happen. It's not sure, maybe squashed, but that's a normal thing. So one possibility that we asked ourselves some years ago, could there be a bouncing? This funnel that becomes longer and longer and longer and narrower and narrower and narrower, when it gets super compressed, could it bounce? Now, think about a falling ball. When it comes up, it's very much similar, its trajectory, as when it's going down, but sort of backward in time. If you take a movie of a falling ball and you project it backward, you see a bouncing up thing. So things that can happen in one way often can happen in a reversed way. So imagine the formation of the black hole and the shrinking of black hole. What would happen if it went back? Well, it turns out that Einstein's theory not only predicts black holes, but also predicts another object, which is exactly a black hole projected backward in time. And a little bit silly name is white hole, because it's sort of the other way around. And a black hole, you can fall in, but not come out. A white hole, you can come out, but not fall in, right? If you have a movie of something falling into a model and you project it backward, you see things coming out of the model. So white holes are also solution of Einstein equations, are also predicted by Einstein equations, like black holes. And in many books, it's written, yeah, they're prediction of Einstein equations, but most likely they don't exist. Except that that's exactly what was written in my book about black holes in the 70s. There's a prediction of Einstein equation, most likely don't exist. So could they exist? And could it be that a black hole forms and then it sort of bounces into a white hole and it comes back? That has been direction of research in which we've been working, I and a lot of colleagues, for the last 5 years or more. I think it's possible. And at least this is the first sketch of the story. And the reason people didn't take white holes seriously is because the question was, how could a white hole form? Unless there is something outside general relativity, it's hard to imagine that things just come out. Come out from what? Okay. But now bring quantum mechanics is. If quantum mechanics can make this bounce, the black hole can make a quantum jump out of a white hole. And quantum mechanics precisely allows these jumps from one solution to the other. This is a well-known quantum mechanical effect. It's called tunnel effect. Some trajectory classical can tunnel in a different classical trajectory. The quintessential example is a wall. There's a trajectory of a ball bouncing. There's another bouncing on the other side. But quantum mechanically, a ball can tunnel through the through the wall and come out. So we use a theory on which, the quantum theory of gravity, on which we are working for all my life, loop quantum gravity, and computed the probability that this happened, and it turns out that it might happen. So here is a possibility. We are inside the black hole. We have been falling to the center. We go to this squeezed, we survived, and then we go through this jump, and now we find ourselves still in the funnel, but now the funnel is not shrinking, it's opening up and coming back. And so we come out. Okay. This is the main idea. It has to be corrected in a number of ways and studied in a number of ways. One of the way this simple bouncing image has to be corrected is the following. Think of a ball. You let it bounce, but it doesn't really come up the same, right? Because it loses friction, loses energy. So you let it go from here, it bounces only from here, the next time from here, because there's dissipation, okay? Second law of thermodynamics, equilibration, dissipation. Sorry, -1 law of thermodynamics when it's here. So same happened for a black hole. A big black hole dissipates. This is a discovery by Stephen Hawking. Emits heat, so it becomes smaller and smaller and smaller. But careful, the surface becomes smaller and smaller and smaller. The inside is still big. So when the bounce happens, the black hole is small because of dissipation. There's a lost energy. Okay? The inside is still big. So if this is correct, and here is the beauty, the theory predicts that all the black holes, assuming there are many whole black holes, they've all become very small, but they still have this big inside, and now slowly, very, very slowly, the inside is coming out. How big? How small? Well, this Hawking theory tells us that the black hole is going to become very, very small and becoming quantum when its size is a certain size that we can compute, and its mass is a certain mass that we can compute, and the mass turned out to be a fraction of a microgram. So if the theory is correct, it might be that there are many little things of the weight of a fraction of a microgram, a very precise weight that can be computed, floating around in the universe, assuming that they were produced in the early universe or so. That's a possibility. Now, it turned out that astronomers see all over the universe something very funny that is called dark matter, which behaves exactly as if it was a powder of little teeny things. So could it be, question mark, that this mysterious dark matter that the astronomers see is just a lot of very small white holes, teeny because they have Hawking evaporated, with this big inside, okay, which are slowly evaporating and they're all floating around us as astronomers. So, I don't know. I hope it is. I hope the answer is yes, because it means that me and my friend will got the Nobel Prize. But, or somebody else measuring that. It's a possibility. Well, that's basically what I want to tell you. And now let's come out, because we have to come out from this teeny thing, so we have to squeeze a lot. So again, imagination. Last detail. Suppose all this is true. First, on what this prediction, this possibility relies? On taking general relativity seriously, so taking Einstein theory seriously, taking quantum mechanics seriously, and struggling to find a coherent story where quantum mechanics and general relativity comes together. And that's exactly the kind of work that Einstein did when he wrote his equation by struggling to put Newton's theory and special relativity together, or what Newton himself did when he put Galileo, parabolas, and Kepler ellipses together. So we know something about the world, and so we built on experience. That's the only source of our knowledge. But experience gives us apparently contradictory story, quantum mechanics, generativity, parabolas, ellipses. And the effort of bringing the apparent contradictory story in a coherent give us an idea of what could happen. And if we're good enough, like Einstein or Newton or others, many others, Maxwell, this gives us a better understanding of reality and predictions that are verified. These little things floating around, if they exist, they could be detected in a laboratory with a sufficient machine, with some quantum technology. I'm not going to that, but in principle, they could be detected. Last detail, then I stop and I want to take questions from you. I don't want to talk more than that. I told you that if you get close to the surface of the black hole, time goes slower. Time is slower down. Obviously, even more inside. So we have gone into black hole. We've been going to the shrinking of the funnel around us. We went through this tunneling, jumped from one, quantum jumped, like electron jumped from one orbit to the orbit in atomic physics. We are outside, we come out. Okay, we squeeze through the small SC. We are out, so we're safe. Well, but careful, how long did this take? Well, it's a simple calculation. I can do a calculation for that. Half an hour. When we come out, outside, billion years have come through. Okay? So that's what this could be. Just a shortcut to the future. You go in and you come out the same place, but far, far away in the future. The universe is fantastic. Let me stop here and take questions.
Thank you so much, Carlo. We have plenty of time for questions, and we'll also be taking questions from online. I'm not sure how that works in practice, but Jessica will convey this to me. So if you have a question, please raise your hand, and we'll bring a microphone to you.
Thank you so much for your lecture. You talked about white holes and how it starts from a singularity and everything comes out of it. Is it possible that the Big Bang could have been a phenomenon like this, and that everything, the prior universe went through a black hole and everything in this universe came out of that white hole?
Yeah, thanks. This is a very good question. Yes and no, in the following sense. The geometry inside a black hole is completely different than the geometry of the universe. So they're two different phenomena. It's not the same phenomenon. Roughly, the universe is homogeneous. Let me just. So it's a three spheres. All directions are the same. If you're inside the universe, it's all points are the same, all directions. So it's very different than the inside of a black hole, where one direction is stretching the other. However, there's a great similarity in what might have happened. Namely, if the loop quantum gravity is correct, this has been studied a lot. There's a very large literature. The most likely thing that has happened at the Big Bang is not sort of the beginning of time, but is also bounce. So the intuition is that you may imagine sort of previous universe being falling on itself, shrinking more and more and more. Once again, Einstein theory in that context would predict that just falls into a point. But you bring quantum mechanics is a sort of pressure. So the universe becomes super concentrated. When the density becomes Planckian, it bounces. So you go through this quantum bounce, And now you see the Big Bang. On the other side, you see the Big Bang. So there is a clear similarity between the two effects. You might even say it's the same sort of effects, the same kind of effects. They're both bounces. But it doesn't mean that we can see the current universe as a white hole coming out. I mean, a ball can bounce and some other thing can bounce, doesn't mean that they're the same thing.
Thank you. I enjoyed that so much. I just want you to pick up exactly where you left off. I'd like to ask, if it takes of the order of magnitude of billions of years for a white hole to form in the time that we live in, is the universe old enough for white holes to have formed in the quantity that would be required to account for dark matter?
Yeah, yeah, I went a bit fast there. It would take billions here, in fact more than billions of years, for a black hole of this size to go through the full process. But the duration of the process depends on the initial size of the hole. So there are two possibilities which are being studied today. One is that in the early phases of the Big Bang, when everything was very hot and agitated, a small black hole formed. So if small black hole formed, they have plenty of time for evaporate, become white hole, and now we see them. That's one possibility. The other possibility, which is more speculative because you need two hypotheses, but maybe it's more interesting, is that if we put together with the previous question, so if the universe itself bounced, then there could be white holes that have formed in the previous phase of the universe and gone through the bounce. And that's something which is being studied by Francesca, by other people here, students, to see whether a bouncy universe might bring with itself some of these things. We don't have enough control of the mathematics for describing this well, so we need strong approximation, but your objection is it's completely... So the big black holes we see are not going to become white hole in our lifetime or haven't had that time in the short life of our universe for doing that, but small one, yes.
No, we won't be able to be heard.
What is it that would come out of a white hole? What would come out of a white hole?
What comes out from the white hole? Good. We have some detailed paper about the kind of radiation we expect to come out. We have some specific predictions about frequency and amplitude. Matteo is smiling. There is a subtlety here. What comes out is basically radiation, like electromagnetic radiation or other. The subtlety is the following. Remember, in this story, seen from the outside, you have a big black hole that forms because things fall inside. And there's a long time this black hole shrinks, so it emits already radiation. Okay, it's a Hawking radiation, and it's very small. And then it's a white hole now, or it's a quantum version of a white hole because it's stabilized by quantum mechanics. It lives a long time, and slowly what is inside comes out. But what comes out is not the energy, because the energy, most of the energy has already come out as heat in Hawking radiation. What comes out, it's a lot of radiation that can carry all the information that fell into the black hole, because the Hawking radiation doesn't carry out the information that was inside. So information means that two different initial states are going to lead to different states. So basically, whatever you bring in, it's badly destroyed, badly, crushed, and what come out is just radiation, which has many possible states, but enough for carrying the information. So that would be a solution also to the so-called black hole information paradox, which is the strange fact that the Hawking radiation most likely doesn't bring out the information that falls inside. So if you want to follow a black hole, memory of you will be in the very weak radiation that comes in the distant future, but very hard to detect, to decipherate.
We do have a question from our online audience. The hole and funnel implies a container. What is the wall of the container composed of?
Can you repeat, please? Sorry. I didn't hear. I didn't hear.
The hole and funnel implies a container. What is the wall of the container composed of?
What is a wall? I'm deaf.
Yeah. I'm going to read it.
The hole and funnel implies a container. What's a wall of the container composed of? Okay. No. No, there's no container. It does not imply a container at all. It's the geometry itself of space which is distorted. That's where imagination is needed. Okay? It's just the container is still the horizon, the surface of the black hole or the white hole. Okay? So here we're still talking about black hole. So the surface, the boundary, is just this sphere. It's just the inside is not a ball. It's something much, much longer. We don't need to imagine this contained in something else. Just imagine there is a sphere, and there is a smaller sphere, but then there's another one like that, another one like that, another one like that, another one like it before shrinking. So there's no container. The difficulty is imagining a curved, non-flat three-dimensional space. We have this intuition that three-dimensional space, it's flat is described by Euclidean geometry. But in fact, we have this intuition because we have been too much at school. And at school, they tell us, X, Y, Z, that's the way space is, and study Euclidean geometry because that's physical space. But that's not true, just false. It's an approximation. It's the same kind of difficulty in which people initially had in thinking that if you're on the Earth and you go that direction and walk, you come back to the other direction. That seems absurd. It's not absurd, just the Earth is a sphere. So geometry can be strange, and our intuition about the fact that inside a ball there is only a fixed volume is just an intuition that has developed in our experience, but is not true in reality in general.
Carlo, I want to ask you to reflect on something that came up in the talk, which is that sometimes in the history of physics, physicists make the mistake of not taking their theories seriously enough. So when the physics shows you something that you have to stretch your imagination to consider as a real possibility, it's sometimes people don't take the theory seriously in that regard. And I'm wondering if you could just reflect on that, because it came up both in the initial response to black holes and then also in the current response to white holes.
It certainly happened with black holes, there's no doubt. In fact, this black hole here, which is Sagittarius A star, it has been recognized being a black hole 10 years ago, 15 years ago, not sure when. And people started thinking that perhaps there are black holes really in the sky. As I said, the first hints were in the 70s. But the signal from this thing here, exactly this one, was was detected on Earth in the 30s of last century. The first time a radio telescope was oriented to the sky. It was somebody working for the Bell Laboratories and was studying communication. There was all this noise in the air, electromagnetic noise, and he built this antenna and he captured a very strange signal. It turned out to come from the star, from Sagittarius constellation. Okay, and soon it was obvious that it came not from anything in our solar system, but from outside, just by timing it. And if people had taken the general relativity seriously, they should have said immediately, oh, this might be sort of the hot stuff around the black hole. Nobody took the theory seriously, and it had to wait 30 years before. So yes, I think you're completely right. General relativity is a very counterintuitive theory, so we resisted believing it. With quantum mechanics, it worked the same. I mean, quantum mechanics was written in the 20s. People realized that things could be entangled pretty soon. What Schrödinger did back in the 20s, early 30s, but nobody believed it. And we had to wait decades before checking, and now the last Nobel Prize was given just by realizing that something was written in the equations 100 years ago is true.
Thank you so much for that talk. Lexicon is funny when you're explaining concept topics. And one of the things I've noticed in your writing is you have this innate ability to distill complex topics to the reader. Today, I really appreciated your use of the word imagination, because imagination is in many ways limitless, but I think also it's binded by the fact that many of us have inherent biases, worldviews, and so we may not be able to imagine everything. In that vein, I wanted to ask you, and this is more of a politically charged question, but how are you, your collaborators, the greater scientific community being more cognizant of the fact that cosmology, physics, astronomy, for the sake of umbrella term, is still a very privileged discipline. And across the globe, it's a very privileged discipline. And across the globe, the top papers that are continuing to be produced are by Western nations. There's a lot of marginalization. We know the academy is not without its flaws, particularly in not recognizing the role of women, marginalized communities. So when you talk about imagination, how important is it, let's say if you're sitting in a room brainstorming, for you to make sure that you're in conversation with people from all demographics, cultures, backgrounds, to be able to talk about worldviews? Here living in Canada, when we talk about Indigenous and First Nations groups, their stories of creation, how they view the world, I think it's important to acknowledge that imagination plays a big role in science. So I think, my question is a bit personal, but from one of the leading experts in the world, I wanted to know what can we do to make sure that we're being more inclusive, collaborative, because, without collaboration, it's, again, that sort of knowledge will be limited to very few. And folks, the incredible advancements that the Western civilization has been able to make has been on the backs of people from Asia, from South America, those civilizations that predate what happened in the Enlightenment, right? All that knowledge that was passed on. So if you could talk, I hope my question made sense. It's a little bit, loaded, but if you could talk about that.
I'll tell you my opinion, breaking in various 2 or 3 steps. One, imagination is, in my opinion, completely crucial in the advancements of our understanding about the world. Science is definitely not just observing, collecting data, writing equation, checking it right or wrong. It's much more complicated operation where you need to form new concepts, to view things differently. And imagination, even in the most direct way, simple, just visual imagination. When you see the way great scientists of the science we have worked, like Faraday or Einstein, they saw things that turned out to be right, and people didn't see before with their mind. First. Second, this kind of imagination is deeply influenced, in my opinion, from the entire cultural environment of a person at all levels. Russian theoretical physics is different than French theoretical physics, which is different than American theoretical physics. I believe that with a good, with not too big errors, if you give me an article, a good article of theoretical physics, without telling me the author, I can tell you this is a Russian, this is a French, this is an American, this is an Italian, okay? From the different ways of, so science is not this abstract, pure things, detached from everything else. Ideas, assumptions, philosophical ways, cultural ways come in. Okay, this is, I think, is not only true in physics; it's all true in all sorts of sciences. There is Francesca teaches a course here in which one of the things that she covers is in biology the effect that a certain number of women had in changing in ethology because they had a completely different perspective on things. So this is the premises. If I look historically, science is slow, in my opinion. It has never been fast. This idea that scientific evolution is fast is completely propaganda. Look, I told you a story that was 100 years old, right? It's just slowly, 70s, 80s, it goes in decades. And historically, we see very clearly that some steps could have been taken by some cultures. Other steps were taken by other cultures. We wouldn't have algebra without somebody in Uzbekistan called Algorithm, who wrote a book whose name is Algebra. I mean, created the basis of what we call now this part of mathematics and so on and so forth. So it seems to me very reasonable that the larger is the diversity of the group of people collaborating into a common aim of better understanding, the better this could work. So that's the direction in which you were suggesting. I'm completely in agreement with what you suggest. My 2 cents is that all this is slow. It's not just something that can be done by fiat in one steps. It takes a slow change. The view of our own society around us about this diversity is constant in evolution, and I think we're witnessing this change.
Please join me in thanking Carlo, and we have a reception that we can move to in the next room afterwards. So thanks so much, Carlo. That was perfect.